Hello friends, welcome to my lecture on Cauchy-Riemann equations. Suppose we have a function, complex function f z equal to u x y plus I v x y, which is differentiable at a point z equal to x plus I y. Then this theorem says that at the point z, that is x y point, the first order partial derivatives of u and b exist. U is a function of x y, v is a function of x y. So, their first order partial derivatives are u x, u y, v x, v y. So, they exist and they satisfy Cauchy-Riemann equations, that is u x equal to v y, or we can say del u by del x equal to del b by del y, and del u by del y is equal to minus del b by del x. So, at each point z where the function f z is differentiable, the partial derivatives u x, u y, v x, v y exists and they are related by these equations. They are known as Cauchy-Riemann equations. So, we can say that whenever the function f z is differentiable at a point z, the Cauchy-Riemann equations are bound to be true. Okay? That means they are necessary for the function to be differentiable at the point z. So, we can let us prove this theorem. Since the function f z is differentiable at the point z, f prime z is equal to limit z, delta z tends to 0, f z plus delta z minus f z over delta z. Okay? Now, if z is equal to x plus I y and delta z is x plus if z is equal to x plus I y, delta z equal to delta x plus I delta y, then z plus delta z is equal to x plus delta x plus I y plus delta y. And so, f z being u x y plus I b x y will give us f z plus delta z equal to u x plus delta x y plus delta y plus I b x plus delta x y plus delta y. Okay. So, f z plus delta z is equal to u x plus delta x y plus delta y plus I b x plus delta x y plus delta y minus u x y minus I v x y, and delta z is delta x plus I delta y. Now, let us take delta z to go to 0 along the path 1, as we had earlier discussed. Here is p, here is q. Okay. We are moving parallel to y axis. After this delta y has become 0, this is your point R, this is x plus delta x y. So, after delta y has become 0, when we move towards p, delta x goes to 0. So, when from q to p we move along the path 1, okay, then when delta y has become 0, delta z becomes equal to delta x. So, f prime z equal to limit delta x goes to 0, u x plus delta x y minus u x y over delta x. Okay. We can rearrange the terms, u x y we can subtract here. So, this is minus this u x plus delta x y minus u x y over delta x plus I times delta limit delta x goes to 0, b x plus delta x y minus b x y over delta x. Now, when delta x goes to 0, you see y has not changed, y remains fixed, there is only increment in x. So, this gives us partial derivative of u with respect to x, and here same this expression when delta x goes to 0 goes to partial derivative of b with respect to x, and therefore, f prime z becomes equal to u x plus I v x. So, along path 1 when we move, we see that f prime z is equal to u x plus I b x. We have assumed that function is differentiable at the point z. So, along whatever path we move to the point z, that is the point p, okay, the limit will have to be same. Okay. So, now let us go to the point p along path 2. Okay. So, when we do that, what happens? So, when delta z goes to 0 along the path 2, this is x plus delta x, y plus delta y, and this is your x, y plus delta y point. Okay. So, we are moving in this like this. Okay. So, after delta x has become 0, okay, when we are moving towards S from Q, okay, when we reach to the point S, what happens? Delta x has become 0. So, when we from S we move towards P, delta y goes to 0. Okay. So, after delta x has become 0, delta z becomes I delta y. So, when delta z goes to 0, delta y will go to 0. So, f prime z will be the limit delta y goes to 0, u x y plus delta y, okay, because delta x has already become 0. So, u x y plus delta y minus u x y divided by I delta y plus limit delta y goes to 0, b x y plus delta y minus b x y over delta y. Now, you can see here x has not changed, x remains fixed, only there is a change in the value of y. So, this gives you partial derivative of u with respect to y. So, 1 over I times this is equal to 1 over I times partial derivative of u with respect to y, and what we get there? Partial derivative of b with respect to y. But 1 over I is minus I. So, minus I u y plus b y. Okay. So, along path 2 f prime z is equal to minus I u y plus b y. Since f prime z exists, both the values must be same. Okay. So, we have u x plus I b x, that is the value of f prime z along path 1. This must be equal to minus I u y plus b y. Okay. Now, equating real and imaginary parts, here real part is u x, here real part is b y. So, u x is equal to b y, and imaginary part here is b x, here imaginary part is minus u y. So, u y must be equal to b x equal to minus u y, or u y must be equal to minus b x. So, thus Cauchy-Riemann equations must hold at the point z if f is to be differentiable at z. If these equations are not satisfied at a point z, then f z cannot be differentiable at z. Okay. So, let us take an example here, f z equal to x plus 4 I y, and show that it is not differentiable at any z. Okay. So, here you can see let z be equal to x plus I y, then f z is equal to u x y plus I b x y. U and b are real and imaginary parts of f z. Now, we are given f z equal to x plus 4 I y. So, what we have? Equating real and imaginary parts, we have u x y equal to x, b x y equal to 4 y. Okay. Now, let us find the partial derivatives here. So, partial derivative of u with respect to x, that is u x is equal to 1, and partial derivative of u with respect to y is 0. Okay. Partial derivative of b with respect to x is 0, and partial derivative of b with respect to y is 4. Okay. Now, you can see here clearly u x is not equal to b y, okay, because u x is 1, b y is 4. Of course, u y is equal to minus b x, okay, because u y is 0, b x is 0. So, u x is not equal to b y for any x y, okay, and u y is equal to minus b x for any x y. So, at any point x y, both the equations do not hold, okay, both the equations must hold at any point x y, and therefore, the CR equations means Cauchy-Riemann equations are not satisfied at any point z, at any point z. Okay. So, the f z is not differentiable for any z. Okay, now we shall see that CR equations, in some cases CR equations will hold at a point, okay, but the function is not differentiable there. Okay. So, it can happen CR equations, the satisfaction of CR equations is a necessary condition for differentiability, it is not sufficient. Okay. So, if a complex function is analytic throughout a domain D, then the real functions u and b satisfy Cauchy-Riemann equations at every point in D. Okay. So, this we have seen. Now, a sufficient condition. Now, suppose the Cauchy-Riemann equations hold at a point x y, then if we want at a point z, then what do we need for the function to be differentiable at the point z. Okay. This theorem gives us the sufficient condition for that. If the real functions u and b of f z satisfy Cauchy-Riemann equations at a point z equal to x plus I y, the function f z may not be analytic at z. However, when we add the condition of continuity to u and b and to the 4 partial derivatives u x, u y, v x and b y, then the function becomes analytic at z. So, at the point z, suppose the 4 partial derivatives u x, u y, b x and b y are continuous together with the continuity of u and b, then the function f z will become analytic at z. So, let us prove this. So, what we so this theorem we have this result we have formalized in this theorem. Suppose the real functions u x y and b x y are continuous and have continuous first order partial derivatives in a domain D. If u and b satisfy Cauchy-Riemann equations at all points of D, then the complex function is f z equal to u x y plus I b x y is analytic in D. Now, in order to prove this theorem, we need the following mean value theorem for real functions of 2 real variables. So, let us look at this real mean value theorem for real valued functions of 2 real variables. Let f x y be continuous and have continuous first order partial derivatives in a domain D. Furthermore, let x naught y naught and x naught plus h y naught plus k be points in D. So, suppose you take any domain in the x y plane, let us take the domain D. Okay. Say one point x y is here, another point is x naught plus h, y naught plus k in D. Okay. So, x naught y naught is here, this is x naught, this is y naught, okay, and x naught plus h, y naught plus k is here, such that the line segment joining these points, this is line segment joining these points, that also lies in D. Then f x naught plus h, y naught plus k minus f x naught y naught is equal to h into f x. F x means partial derivative of f with respect to x, and similarly f y is partial derivative of f with respect to y. So, h times f x plus k times f y, the partial derivatives f x and f y are being evaluated at a suitable point of that segment. So, some point is there, say this, suppose this x naught y naught we denote by p and x naught plus h, y naught plus k we denote by q, then there is some point, let us say r, okay, in between x naught y naught and x naught plus h, y naught plus k, such that f x naught plus h, y naught plus k minus f x naught y naught equal to h times f x plus k f y, where f x and f y are evaluated at r. Okay. So, I can write like this, this is equal to h times f x at r plus k times f y at r. There is some point r in between x naught y naught and x naught plus h, y naught plus k, where f x and f y are being evaluated. Okay. So, this is the mean value theorem for functions of 2 variables. We are going to use this in order to prove the sufficient condition for analyticity. So, let us take a p to be any fixed point in D. Suppose you take any fixed point, let us take a domain D. Okay. Let us take a fixed point p here, its coordinates are x, y. Since D is a domain, okay, it contains a neighborhood of the point P. Okay. So, let us choose a point Q in that neighborhood. You take a neighborhood of this. So, let us take a point Q in this neighborhood. Okay. What we have, it is x plus delta x, y plus delta y. So, in the neighborhood of P, Let's take a point Q here. Okay, let us choose a point Q, x plus delta x, y plus delta y in the neighborhood such that the straight line segment PQ, this PQ, okay, is in D. Then by mean value theorem, ux plus delta x, y plus delta y minus uxy is equal to delta x into ux at m1, delta y uy at m1. m1 is some point in between P and Q. Okay. So, let us draw this figure. This is your point P, here is a point Q, this is x y, this is x plus delta x, y plus delta y. In between P and Q there is a point, let us say m1. Okay. There is a point m1 at which we have ux plus delta x, y plus delta y minus uxy equal to delta x ux at m1, delta y uy at m1. And similarly for the function vxy, we have bx plus delta x, y plus delta y minus bxy equal to delta x, the partial derivative of b with respect to x at m2 plus delta y partial derivative of v with respect to y. So, at the point m2. So, that we have, so this is, there is another point m2 here, okay, at which, so see what we have to mean, I mean that ux plus delta x, y plus delta y minus uxy, there exists some point m1 in between P and Q at which we have this. Okay, for the real function uxy we have this, and similarly for the real function vxy we have . Okay, for some point m2 in between P and Q. Okay, so so we have these two equations where the partial derivatives are being evaluated at some suitable points m1 and m2 of the line segment PQ. Now using the Cauchy-Riemann equations, now delta f, the increment in f, delta f is the difference fz plus delta z minus fz. Fz plus delta z is ux plus delta x, y plus delta y plus ib x plus delta x, y plus delta y. Fz is uxy plus ibxy. So, we have written the value of fz plus delta z minus fz here. Now, we put the value of ux plus delta x, y plus delta y minus uxy here from the previous slide, from here, okay. And similarly from here we put the value of the other difference, okay. So, we have delta x, delta u by delta x m1 plus I delta y delta u, okay. So, what we have u x plus delta x, let me write it, okay. So, let me clarify this. See, we have delta f equal to what we have fz plus delta z minus fz. So, this we can write as u x plus delta x, y plus delta y, okay, plus I b x plus delta x, y plus delta y minus u x y minus I b x y, okay, putting the value of fz and fz plus delta z and fz, we have this. Now, let us write u x plus delta x, y plus delta y minus u x y plus I times b x plus delta x, y plus delta y minus b x y. Okay. So, this is delta x u x at m1 plus delta y uy at m1 plus I times here we have delta x bx at m2 plus delta y by at m2. Okay. So, what we do now, let us look at this. So, here we have written delta x delta u by delta x m1. Okay. We are using actually Cauchy-Riemann equations here. So, what we do is in this term we are making use of ux equal to by and uy equal to minus bx. All the derivatives which were there with respect to y are being changed to partial derivatives with respect to x. So, let us do that. So, what do we do? Partial derivative of v with respect to y using ux equal to by and uy equal to bx minus bx. Okay. What we will get? This will be equal to delta x delta u by delta x m1, and here we will get I delta y by at m2, by at m2 will be ux at m2. Okay. And then what we will get? I times, here let us see, delta x delta b by delta x m2. Okay. Now, here we have delta y u by at m1, u by at m1 will be equal to minus bx at m1. Okay. So, minus bx at m1 I can write as I times into delta y. Why? Because iota into iota is minus 1, iota square is minus 1. So, u by at m1 is minus bx at m1. So, this term will become minus delta by bx at m1, and that minus delta by bx at m1 I have put here because this is I square. So, I square is minus 1. So, this is minus bx m1 into delta y. Okay. So, this is how we come to this term. This is what we get, okay, using Cauchy-Riemann equations. Now, let us see delta z equal to delta x plus I delta y. So, I can write it as delta x ux at m1. This you see here what I do, I add iota delta y ux at m1 and iota delta y ux at m1 I subtract. Okay. So, if I do that, actually what I do, delta x plus I delta y I add I delta y ux at m1 and I subtract that. This is what I do. Okay. So, here I add iota delta y ux at m1 and I subtract iota delta y ux at m1 and I get this term. Okay. Then iota delta z. So, here also I add iota delta y, okay, and I subtract iota delta y. So, delta x plus iota delta y will become delta z partial derivative of b with respect to x. Okay. What I do is this term delta z delta, okay, here I add let me write this term. Okay. So, delta x bx, okay, this is delta x bx m2 and then I add delta x here. So, I make it delta z bx at m1 and I subtract delta x bx at m1. Okay. So, delta z bx at m1 is here, okay, and then delta x times bx at m2 minus bx at m1 is here. Okay. So, this is what we do, and then let us take the limit of So, delta f over delta z, as delta z goes to 0, for that what you do, divide both sides by delta z. When you divide by delta z, delta f by delta z, okay, with what you get, this is equal to u x at m1 plus iota delta y over delta z, u x at m2 minus u x at m1 plus iota, this is delta z, when we divide this becomes 1. So, b x at m1, okay, and then delta x by delta z, b x at m2 minus b x at m1, okay, this is what we get. Okay. So, when delta z will go to 0, what will happen? Mod of delta y, see delta z is delta x plus I delta y. So, delta y is always less than or equal to mod of delta y is always less than or equal to mod of delta z, which is under root delta x whole square plus delta y whole square, and also and similarly mod of delta x is always less than or equal to mod of delta z. Okay. So, what will happen? Mod of delta y over mod of delta z is less than or equal to 1. So, delta, when we divide by delta z, okay, delta y over delta z is bounded by 1, and here delta x by delta z is bounded by 1, and when delta z goes to 0, the m1 and m2 points will tend to the point P. So, the partial derivatives by the continuity of the partial derivatives u x at m2, u x at m1, they will change, they will tend to u x at P, and this will also tend to u x at P. So, this will be 0, and here we will have partial derivative of b with respect to x at P. Here we will have partial derivative of u with respect to x at P, and this will be partial derivative of b with respect to x at P. This will be partial derivative of v with respect to x at P. So, this will also be 0, and delta x over delta z is bounded by 1. So, what I do is when we divide by delta z, we get the following actually. So, delta f by delta z, okay, limit delta z tends to 0, when we do, this is what we get, limit delta z tends to 0, okay, partial derivative of u with respect to x at m1 we have, then limit delta z tends to 0, iota times delta b over delta x at m1. So, they will tend to partial derivatives of u at the point P plus partial derivative of b with respect to x at the point P. The other derivatives will tend to the correspective derivatives at the point P and will cancel. Okay. So, this happens because of the fact that mod of delta x over delta z is less than or equal to 1, mod of delta y over delta z less than or equal to 1, and the continuity of the partial derivatives of u x and b x. So, what will happen then? F prime z exists at an arbitrary point P of D, and therefore, f z is analytic in D. Now, let us consider the Cauchy-Riemann equations in polar form. So, if z is equal to r cos theta plus I r sin theta, then we have f z equal to u x y plus I b x y. So, if we use the polar coordinates r theta, then we know that the partial derivatives, the Cartesian coordinates x y and the polar coordinates r theta are related by x equal to r cos theta and y equal to r sin theta. Okay. So, x y depend on r and theta. So, I can say that u is a function of r theta, okay, when we replace z by r e to the power I theta. Okay. So, u is a function of r theta and b is a function of r theta. So, in this article we shall be finding the corresponding Cauchy-Riemann equations in the polar coordinates r and theta, and we see that they are u r equal to 1 over r b theta. U r is the partial derivative of u with respect to r, b theta is the partial derivative of b with respect to theta. Similarly, v r is the partial derivative of b with respect to r minus 1 over r partial derivative of u with respect to theta. So, let us now see how we derive them. Okay, so, let us see, we have u is a function of x by x is a function of r cos theta r and theta, by is a function of r and theta, and these give you r square equal to x square plus y square and theta equal to tan inverse y over x. Now, r square equal to x square plus y square gives you 2r rx equal to 2x. Okay. So, rx, which is partial derivative of r with respect to x, is x over r, and this is equal to cos theta. Similarly, 2r delta r over delta y equal to 2y. Okay. So, ry equal to y over r, which is equal to sin theta. Okay. So, ux by chain rule, partial derivative of u with respect to x is given by partial derivative of u with respect to r into rx plus partial derivative of u with respect to theta into theta x. Okay. So, we need to find theta x and theta y also. So, partial derivative of theta with respect to x will be partial derivative of tan inverse y over x with respect to x, and this is 1 over 1 plus y over x whole square into minus y over x square. So, this will be equal to x square upon x square plus y square and minus y upon x square. So, this will give you minus r sin theta, I r sin theta, y is r sin theta divided by r square. So, this is equal to minus sin theta over r. Okay. So, partial derivative of u with respect to x is u r into rx, rx is cos theta. So, we get this, and then minus sin partial derivative of theta with respect to x is minus sin theta over r. So, minus sin theta over r u theta. So, we get this first equation. Similarly, let us find uy. Uy is so what we have ry equal to sin theta. So, we have sin theta into ur. Okay. And then u theta, let us find theta y. Theta y we can find in similarly like we have formed theta x. So, theta y is equal to partial derivative of tan inverse y over x with respect to y, which is 1 upon 1 plus y by x whole square into 1 over x. So, this is x square over x square plus y square into 1 over x. So, this will give you x upon x square plus y square. So, r cos theta divided by r square. So, we get cos theta divided by r. Okay. So, we get this. Okay. So, sin uy equal to sin theta into ur plus u theta into cos theta by r. Now, similarly, we can write the expressions for the bx and by, only we have to replace u by b. So, bx equal to cos theta vr minus sin theta over r b theta, and by is sin theta ur br plus cos theta over r b theta. Now, what we do? So, ux equal to by, ux equal to by gives cos theta ur minus sin theta over r u theta equal to sin theta br plus cos theta over r b theta. Okay. This is ux equal to by. Uy equal to minus bx gives what? Uy is sin theta u r, okay, plus cos theta over r, u theta equal to minus u by equal to minus b x. So, b minus b x means minus cos theta b r plus sin theta over r b theta. Okay. Call it equation number 1 and this as equation number 2. Now, what you do, multiply equation 1 by cos theta and 2 by sin theta. Okay. So, 1 into cos theta and 2 into sin theta. Okay. Then give you what? You see, cos square theta u r plus sin square theta u r, which will be equal to u r. So, u r, and then here what will have? Minus sin theta cos theta over r u theta. Here we will have sin theta cos theta over r u theta. So, they will cancel. We are multiplying equation 1 by cos theta, equation 2 by sin theta and adding. So, this will become 0. The right side will be equal to cos theta sin theta b r. Here we will have minus sin theta cos theta b r. So, that will also cancel. Here we will have a cos square theta over r b theta. Here we will have sin square over r b theta. So, when we add, we get 1 over r b theta. So, this is one Cauchy-Riemann equation in polar form. The other Cauchy-Riemann equation, if we want, then what we do? Now, we multiply equation 1 by sin theta. Okay. So, equation 1 by sin theta. So, we get sin theta cos theta u r here, and here we multiply by cos theta and subtract. Okay. So, minus 2 times cos theta. Okay. So, we multiply 1 by sin theta, 2 by cos theta and subtract. Then what will happen? Sin theta cos theta u r, sin theta cos theta u r will cancel. Here we have minus sin square theta by r. Okay. Here we have minus cos square theta by r. Okay. Sin square theta by r, cos square theta by r will give us minus 1 over r u theta. So, this will give you minus 1 over r u theta, and here right side what will happen? Sin square theta b r and then plus cos square theta b r, because we are subtracting. So, that will give you b r. The other term will be sin theta cos theta over r b theta minus sin theta cos theta over r b theta, that will cancel. So, we will get this equation, okay, this equation and this equation. Okay. They are the Cauchy-Riemann equations in the polar form. Okay. Now, let us consider use these Cauchy-Riemann equations in polar form to see whether they are satisfied for a complex function. So, let us say f z equal to z cube. Okay. Taking z equal to r cos theta plus I r sin theta, what we will get? F z equal to z cube will give us r cos theta plus I sin theta whole cube. Okay. This is r cube and cos theta plus I sin theta whole cube. So, by de Moivre's theorem I can write cos 3 theta plus I sin 3 theta. R I can say using using the Euler's formula, z equal to r cos theta plus I sin theta, I can write as r e to the power I theta. So, this will give you z cube equal to r cube e raised to the power I theta to the power 3, which is r cube e raised to the power 3 I theta. So, again r cube into e to the power 3 I theta is cos 3 theta plus I sin 3 theta. So, f z equal to r cube cos 3 theta plus I sin 3 theta. So, here u is equal to f z is equal to u r theta plus I b r theta. Okay. So, this is equal to r cube cos 3 theta plus I sin 3 theta. So, equating real and imaginary parts, u r theta equal to r cube cos 3 theta and b r theta equal to r cube sin 3 theta. Now, let us find u r is equal to 3 r square cos 3 theta. Okay. So, this is u r, and b theta is what? If you find b theta, sin 3 theta, when we differentiate we get 3 cos 3 theta. So, 3 r cube cos 3 theta. So, b theta over r, okay, this gives 1 over r b theta equal to 3 r square cos 3 theta, which is equal to u r. Okay. So, u r is equal to 1 over r b theta. Okay. Similarly, b r is equal to 3 r square sin 3 theta. This is b r, and we find u theta is equal to minus 3 r cube sin 3 theta. When we divide by r, we get minus 3 r square sin 3 theta. So, when we multiply by minus 1, we get 3 r square sin 3 theta. So, the b r is equal to this. Hence, u and b satisfy C R equations in polar form, and so f z equal to z cube. These are valid at any point z of the complex plane. So, f z equal to z cube is analytic for all z not equal to 0. See, why we are saying this? Because the partial derivatives, the functions u r theta, v r theta, and their partial derivatives u r, b r, they are all continuous functions of r and theta. So, by the sufficient conditions for analyticity theorem, okay, by that theorem f z equal to z cube is analytic for all z, because not just the fact that u and b satisfy Cauchy-Riemann equations, f z is equal to z cube is analytic. It follows because of the continuity of u and b and the partial derivatives of u and b with respect to r and theta. So, f z equal to z cube is also analytic. Okay. Now, here when you use the Cauchy-Riemann equations, you see that we are dividing by r, that means r cannot be 0. So, Cauchy-Riemann equations here can be used only for all z which are not equal to 0, because z equal to 0 means the origin point. Okay. So, from this validity of Cauchy-Riemann equations, we can simply say that f z equal to z cube is analytic for all z not equal to 0. For the z equal to 0 point, we have to separately see. Okay. So, f z equal to z cube is also analytic at z equal to 0, that we can see by definition of derivative. Okay. We can easily show that f z equal to z cube is differentiable at z equal to 0. So, it is differentiable in any neighborhood of z equal to 0, because at all non-zero z, okay, f z equal to z cube satisfies C R equations in polar form, and its first order partial derivatives together with u and b are continuous. So, it is analytic for all z belonging to C. Now, relation between complex analysis and Laplace equation in 2 dimensions. Okay, 2D, this D means dimension, 2-dimensional case. So, first later on we shall show that derivative of an analytic function is itself analytic. Okay. If f z is an analytic function in a domain D, then f prime z is analytic in D, and when f prime z is analytic in D, f double prime z is analytic in D. So, all ordered derivatives of f z exist, and they are analytic functions in D. This we do not have, this kind of result we do not have in real calculus. There we know that if the function f x is differentiable at a point x equal to x naught, then f double prime x need not exist, okay, at x equal to x naught. But here if the function is analytic at z naught of then it is its all ordered derivatives are also analytic at z naught. So, because of that, if f z is equal to u x y plus I b x y, okay, we have seen that if f z is analytic and f z is equal to u x y plus I b x y, then f prime z is u x plus I b x. Okay. So, if f z is analytic at any point z, then what will happen? F prime z, f double prime z, they are also analytic. So, that means they are all differentiable functions. Differentiable functions are continuous functions. So, u x v x will be continuous, okay, u y b y will be continuous, because u x v x are related to u y b y by Cauchy-Riemann equations. So, u x v x are continuous, so u y b y will be continuous. So, all derivatives, first order derivatives will be continuous. F prime z is analytic means f double prime z is analytic. So, second order partial derivatives f double prime z we can write as, because this is a real part of u f prime z. So, we can write like this, and so on. So, second order partial derivatives are also continuous. So, continuing like this, all ordered partial derivatives, okay, of u and b exist, they are continuous functions. So, in particular u x y and b x y will have partial derivatives of second order partial derivatives which are continuous, and when second order partial derivatives of a real valued function of two real variables is continuous, then the order of differentiation can be interchanged, this we know. So, u y x is equal to u x y, and similarly b x y equal to b y x. Now, we have when the function is analytic, we have u x equal to b y, u y equal to minus b x. So, when you pick up the equation u x equal to b y, that is this, differentiating with respect to x, because u is a function of x y. So, its partial derivative with respect to x is also a function of x y. So, I can again differentiate it with respect to x. So, when we differentiated this with respect to x, I get this, I get this. Similarly, the other equation is u y equal to this one, u y equal to minus b x. If this is r, I can say this. So, if I differentiate it with respect to y, what I get? Second derivative of u with respect to y, okay, is equal to now let us call this as equation 1, this as equation 2. So, adding 1 and 2, okay, what we will get? U x x plus u y y, okay, equal to partial derivative of v with respect to y first, then with respect to x, and here partial derivative of b with respect to x first, then with respect to y. Their sum is equal to 0. This minus this is equal to 0 because of this, okay. So, this gives you the Laplacian of u equal to 0. Laplacian del square is defined like this, del square be defined as in 2 dimensions. So, del square u equal to 0, and here we have shown that del square b equal to 0. Just similar, we can similarly do here what I did, I differentiated this with respect to y. So, I get b y y, okay, I get this, and then I differentiated with respect to x. So, I get this. So, minus, okay, and this I can call as 3, this as 4. Then I subtract 4 from 3, okay. So, 3 minus 4, 3 minus 4 will give us b y y plus b x x, and here this minus this minus this is 0 because of this, okay. So, del square b equal to 0, and like we have similarly del square equal to 0, this we have already seen. So, u and b have second order partial derivatives which are continuous, and they satisfy Laplace equation in 2 dimensions, okay. They are solutions of Laplace equation in 2 dimensions. So, they are harmonic functions. The real and imaginary parts of an analytic function in a domain D are the solutions of 2 dimensional Laplace equation and have continuous second order partial derivatives. We shall see that when we have the third lecture, in the next lecture, when we define the harmonic functions. We shall see that the real and imaginary parts of this analytic function, an analytic function, are harmonic functions in D, okay. And this property of analytic functions is very important, has a great practical importance in engineering mathematics, as we shall see in our next lecture. Thank you very much for your attention.